So far we have discussed about the different modalities of edge. Now we are going to discuss in detail about the detection of edge. Here is a very simple image and a plot of horizontal row, which is denoted by this red line. If we just take a row and plot it, and we would see it starts out high and then comes down smoothly and it goes back up high again. We can see here it starts with high and goes down, and again it goes up smoothly. And if we apply a derivative to that function, if we apply a derivative to this function, and we will get a function that looks like this. And so this is the function, this is the first derivative of that scan line, and the edges where intensity profile changes rapidly in the original image correspond to these extrema of the derivative. We can see here this is the first derivative of this intensity function, and the edge corresponds to the edge correspond to the extrema of derivative, and these are the extrema of derivative, and this occurs where the intensity profile changes. So finding edge is going to have something to do with the finding peaks in the derivative. Now question arises, how we are going to find the extrema in the derivative. So we're going to filter our image with the appropriate operator in order to find the peaks in the derivative. So differential so let's talk about differential operators. Differential operator, when applied to an image, returns some derivative. We can model these operators as max kernel that compute the image gradient function, and we threshold this gradient function to select the edge pixels. Now question again arises, what is gradient? In multivariate calculus we have a function of more than one variables, and where we can take partial derivative, the partial derivative in x direction and derivative in y direction. We can see here the image. In first image we can see the partial derivative along x direction, because the changes occur only in x direction. Then if we take the partial derivative in, there is no changes in y direction, so it gives only the partial we can just get the partial derivative along x direction. In second figure we can see this gives the partial derivative along y direction, and here we can see the changes occurs only along the y direction. And but in image we have change along x direction as well as in y direction. So the gradient consists of the gradient is a vector. So we take the partial derivative along x direction and y direction. So the gradient is a vector that is made up of those derivatives, means it is the vector that is made up of the derivative along x direction as well as in y direction. And in image we have two vector made up of f, partial of f with respect to x, and the partial of image in y direction. So here is the gradient, and the magnitude of this gradient is given by the sum of square root of the magnitude is given by the square root of sum of square of this gradient, and the direction is given by the ratio tan inverse of ratio of magnitude of gradient along y direction and magnitude of gradient along x direction, or derivative along ratio of derivative along y direction and derivative along x direction. And to save computation, the magnitude of gradient is approximated by this. We take the modulus of mx, and we take the sum of absolute value of mx and absolute value of my. Now let's talk about the discrete gradient. In continuous math, the partial of f with respect to x is just limit given by this expression. Here it's given by this expression, and what we see here is we move little bit in x direction, that is epsilon, and subtract the original one, this fxy, and divide by epsilon, and when we let the limit go to 0, that becomes our derivative. This is our derivative in x direction. But in discrete math, but discrete world, we can't move arbitrarily close, so we have to take what we call the finite difference. So what we are going to do is we are going to take about approximating our partial by some finite difference. So the simplest finite difference is of this form. Here we take one step in x direction and see what the value of function is, and we subtract of the original and divide how big it was, the step. So the step is just 1, so it looks like this. That is, we go x for a finite difference in x direction, we go the one step forward in x direction and subtract the original 1 and get the finite difference. So now we can see here the response of finite difference in image. In first image, what we do is we go a step forward and subtract the left one and get the response. Here what we have seen is the changes. We can see the it detects the changes along x direction only, so we can see the mostly the vertical strips in this image. Similarly, in this image, in right side, we can see this detects the horizontal strips. That means we can see the horizontal strips. That means it detects the edges or along the y direction, and we can take the magnitude of these two, and which we take by the sum of squares, and take the sum of squares and take the square root, and we will end up with this image. And this picture is this picture gives us the edge of an image. This final picture gives us the edge of an image. So so far we are just talking about the discrete gradient. Now what we need is the operator. We want to mask our kernel that we want a mask or kernel that can implement these gradients. So here is an example of an operator H. This is an operator. We use 3 rows, and for now we have only 2 columns. Since it doesn't have the middle pixels, it cannot be taken as a good operator, since it takes a value from right and subtract the left one. And the question arises, what is the special about right? We can also go to left. So if we want to do that, what can we do? And the answer comes with this solution. We can do an operation which looks like this operator. We can use another operator, that is H. which now again question arises why there is +1 and -1, minus +1 by 2 and -1 by 2, and it's the average of right derivative and the left derivative. What we mean is that by this the right derivative would be a +1 here and -1, like we can see here. The right derivative is the +1 here and -1 here, and the left derivative would be +1 here and -1 here. And what we do is we take the average of these two by dividing, we take the sum and divide it by 2, and we get this operator. So we end up with this operator. So now here what we get is we get the operator gives the average of, this operator gives the average of left and right. So this includes the left operator as well as the left derivative as well as the left derivative. Now it ends up with this. Now this is our final operator with the -1 by 2, 0 and +1 by 2, and this operator gives us the average of left and right derivative. Now people have been doing derivatives and edges for a very long time, and the most classic one is referred to as a Sobol operator. Sobol operator, it just looks like the same what we have discussed before, but instead of that positive 1/2 and negative 1/2, there is a multiplication by 1 by 8, and we can see that it does not only it doesn't consist only plus it doesn't consist only +2 and -2, which you divide them by 4 and we get the same value, but it also does +1 and -1 in the row above and below. And the idea here is that if I am talking about if I am taking a derivative, we assume that our images are sort of locally smooth, that is, they change similarly along in locally. So the idea here is that if I am going to compute the derivative at a pixel, I won't look just left and right of me, but also look nearby me, and then I normalize this thing by dividing it by 8. What we do is, like, I just don't consider by taking only along this direction, left and right. I also think about nearby me or neighbors of me by taking the pixel above me and below me. So it ends up with this mask along x direction, and for y direction it ends up with this one. And this is the Sobol gradient. It also consists of gradient along x direction and gradient along y direction, and the magnitude is the sum of squares, and take the square root of that sum of square, and the angle is given by arctan 2 gy gx. And here is the example we get here, like the original image here, and the gradient magnitude and the thresholded gradient magnitude. And there are some well-known gradient masks. Here is the Sobol, as we have just discussed before, and in Prewitt it just takes the difference along x direction, taking the consideration of its neighbors, and in y direction also. And the robots consider the diagonal neighbors. And in Sobol, what we can see here is it gives importance to the center pixel. while in Previtt it is just the plane operator, we can say it the plane operator, but in Sobel it considers the center pixels while taking the gradient.